Welcome back. Now we have to solve the optimization problem that we formalized before. Some people might still ask, why we should solve that problem. Remember, that problem is based on the large margin bound. If you haven't seen it before, watch the previous videos. The large margin bound proves a tighter learning bound. And it is the origin for the support vector machines. What is a support vector machine? It's basically an algorithm that builds up the best hyperplane to divide a binary sample. Wow, it's interesting. Doesn't matter, let's close this. Sorry guys. To divide a sample. It's exactly that. Builds up the best hyperplane. By best, I mean the hyperplane whose margin is the greatest as possible for my sample, for my data sample. There is something really important here. You are going to see many solutions for this problem. There are a bunch of optimization algorithms that people use. The classification algorithms that people use. For example, people use naive Bayes, multi-layer perceptron, the perceptron, random forest, ID3, C4.5, and goes on and on, like deep learning. But there is something really important. If you've got a linearly separable space, that means I can separate the positive and negative classes in a given space. The support vector machine provides the best solution at all. And the large margin bound is the proof for that. What happens if I don't have that space? I need to come up with some space. What happens when I'm using like some deep learning strategy? It is just building up some space transformation to find the best possible way of separating classes, separating examples belonging to different classes. That's quite important. So again, when we talk about support vector machines, we are looking for the best algorithm we can find. Of course, that depends on the space, and that requires space transformations or kernelizations. You can also see this from a different perspective. The large margin bound is one of the most important results we've got with the statistical learning theory, after the statistical learning theory. Why one of the most important results? Because it provides this result that we've got tighter learning bounds or stronger learning guarantees, stronger uniform convergence if the margin is the greatest as possible for a given data sample or for a given problem, even to be, more general and of course more specific. More general, not more specific. What is the problem that stays? The problem that stays now is we have the formulation for the optimization problem as seen in the previous video. But how can we solve it? You guys probably remember that my problem is something like this. Something like minimize half times the norm of vector w to the square, okay, subject to my restrictions. Subject to yi, which is a class label, times the dot product of my w vector by some input xi plus some b must be greater or equal to 1. This is my optimization problem. This is, to be more specific, this is the support vector machine optimization problem. If I solve it, I will have the solution, just the solution for the best algorithm. Just the solution for the best algorithm in the literature. Okay? Of course, that algorithm depends on my space being linearly separable, and we are going to discuss kernels later. You guys have got some sort of sense on kernels from my previous video. Actually, from I think 2 videos back, or 1 video back. I'm not sure. I think it's like 2 videos back, in which we defined a bidimensional space and then a 3-dimensional space, and then you're assessing how a single hyperplane could shatter, could divide my input space. What is interesting about this is I have to remember the Lagrange multipliers. Why? Because the Lagrange multipliers help us actually to solve problems for in which constraints are defined in terms of equalities. I could say that if my problem, if it were like this in terms of equality, I could solve it using Lagrange multipliers, but it's not. Actually, it is in terms of what? Greater or equals to 1. What should I understand to solve it? I should remember or study for the first time the Karush-Kohn-Tucker multipliers. Okay? Actually, this will be the solution for this problem whose constraints are defined in terms of greater than or equal to something. But of course, to discuss on the Karush-Kohn-Tucker multipliers, we need to remember the Lagrange multipliers, because this is a foundation, this is a basis for the KKT multipliers, as it is known. Okay, Karush-Kohn-Tucker. Let's go back to this segment of our class, just to have a big picture. What is and what's like the Lagrange multipliers? It is named after Joseph Louis Lagrange, who was a guy that studied this kind of problem, this kind of optimization problem, in which we are trying to solve either a minimization or a maximization problem in terms of some equality. Here we've got some constraint equals to C. Okay? This is just an example in which we've got some optimization function. That's the name we give for this f of x, y. It's an optimization function in kind of bluish gray, I'm not sure. Okay? And here we've got a constraint, g of x, y. This constraint could be, for instance, this linear constraint in red. So if I am trying to maximize, you guys can notice that if I'm trying to maximize for the equality means a point from this surface bluish surface that somehow touches my constraint, because I have to be equal to my constraint. You guys can see that here we touch it with this kind of elliptical function. It touches here. Of course, it touches over here, over here. And of course, the maximal value for the surface that touches this red function is exactly in here. That's a place where it touches, okay? Exactly this function. So for this problem, my solution would be exactly on my mouse over here, okay? On the point over here. That's a way of seeing the Lagrange multipliers. So every optimization problem in which I've got this form I can work with, but there is like some conditions. Let's discuss on the conditions. First of all, take a look what's happening over here. In blue, we've got the optimization problem, okay? The optimization function f of x, y, and in red, we've got the constraint. This is the space in terms of x and in terms of variable y, and we are just looking at the contour lines just to make it easier. You know what's amazing about Joseph Louis Lagrange? He found that the exact point, or the points in which the gradients of my optimization function and the gradient of my constraint function turn out to be equal, given some correction lambda. In this case, I'm just writing it as minus lambda. It could be written as plus lambda. We are going to discuss that later, doesn't matter. But the point in which I have the gradient vector of f equals to the gradient vector of my constraint g, given some correction, some scalar value providing the correction, is a candidate solution point. Is a candidate solution. You guys can see that those vectors here just show me the gradient vectors. Take a look at those gradient vectors in blue and those gradient vectors in red. You can notice that this gradient vector turns out to be equal to this gradient vector being multiplied by some lambda, in this case, of course, some negative lambda. So if I flip this vector to the other side, if I reflect it to the other side, I can make it equal. Why? Because they are parallel vectors. So the point here is Lagrange found that parallel vectors, parallel gradient vectors, provide points to be analyzed in my problem. Every point whose gradient vectors can cancel out each other is a point to be assessed, is a point to be later analyzed, and we can understand if that point is indeed a solution or just a candidate solution. That's like amazing about his study, and really, really interesting. Oh, I just provide you guys like an example, a demonstration here using I think Mathematica. You know why? You know what? I think I've got that here. Let's find it. I think it's like in here, Lagrange.ogv. Maybe over here, let's see. Where is it? Maybe over there, no. Maybe, just maybe. Let's see if it is here in my backup files. I think it's over here probably. My backup files could be there. Let's see. Yeah, let's try. Maybe it's there. No, it's not. Let's see over here. it doesn't matter. It's just a video. You guys can see this demonstration. I can also share it with you guys later, and you can just play it. It's just a video. You can play it using like MPlayer or any kind of player you guys decide to use. You know why it is interesting? Because it's going to show exactly those parallel vectors being found. Just a nice example. But actually, we can go for a practical example. Take a look at this. This is a problem we wish to solve. Maximize this linear function x plus y. X plus y is my optimization function. It is this surface, this linear plane you guys can see here. It's a plane. X plus y. X is showing this axis and y on this different ways, axis over here. Of course, the result of x plus y is shown in z over here, in this axis, okay? And subject to a given constraint, my constraint is x to the square plus y to the square must be equals to 1. So if I have a constraint that's defined in equality terms like this, I can use the Lagrange multipliers after analyzing a list of points, so to speak. We're going to analyze the list of points, don't worry. Take a look at the constraint. When I see the constraint, by the way, I can see the constraint if I plot it like this. This is the constraint. X to the square plus y to the square equals to 1 is the same as a circle in terms of x and y. It is here. How can I find the solution using Lagrange multipliers? Lagrange multipliers does something that's quite interesting. It's going to project this restriction, this constraint in terms of x and y into my surface like this. This is the projection, as you guys can see, just the projection. As you remember, I can only solve this for the equality. Where are the points of my surface that are equal to my constraint? If my constraint is in here, the points, of course, are those points over there, are those points for x and y here that provides different values in terms of z. Of course, here I have the smallest as possible value for z, and here I have the greatest as possible value for z. There is a small catch here. I can only employ Lagrange multipliers if f and g are differentiable. Can I proceed with the the gradient vector? Can I find the gradient vectors for the gradient vector for f and for g? Yeah, I can. I can. Why? Because I can differentiate those two functions. So yes, if I say no, I cannot solve the Lagrange multipliers. Okay. Does it consider one or more equality constraints? Yeah. Yeah. It considers a single equality constraint. If it considers an inequality constraint, I cannot use Lagrange multipliers. I cannot. The gradient of g is different of the zero vector. That's another point. If the gradient of my constraint is different from the zero vector, I can solve my problem. Otherwise, I can't, because I will have an infinite number of solutions. We can discuss that later, or you guys can. I'm going to show you like some references for that. Let's solve this problem. How can I solve it? I should basically take my problem. My problem is in here. Maximize this optimization function x plus y, which is this surface, okay, illustrated by the surface, subject to this constraint. And the constraint is plotted in terms of x and y, as you guys see here, and Lagrange multipliers will project. Not project, I mean, not in that way, but it will result in the same as a projection we are showing here. This is just an illustration, of course. How can I solve it? This solution for a Lagrange multiplier problem is basically the gradient of my optimization function has to be equal to the gradient of my constraint function multiplied by some lambda. I'm using a negative lambda, as I showed you guys, as we discussed before. Could be a positive lambda in this formulation, in this way of formulating. But we can discuss that later. It doesn't matter now. And our constraint function has to be equal to 0. This is the linear system that I need to solve to find the solution using Lagrangian multipliers. This lambda is what we call a Lagrange multiplier. Okay? We're going to talk about that really soon. How can I find the gradient vector of f? If I take f, which is in here, x plus y, when I differentiate in terms of x, I will have 1x, as you guys see here. When I differentiate in terms of y, I will have 1 here and 0 here, because this will be a constant. So you have the vector 1, 1. This has to be equal to minus lambda, and I have to differentiate this in terms of x. That will be 2x. This will be 0, this will be 0. And if you guys don't remember differentiation, please go back to a calculus book and study it before. This will be 2x. If I differentiate this in terms of y, it will be 0, 2y, and 0. That will be 2y, as you can see over here. And I have to make my constraint equals to 0. To make it equals to 0, I just bring this 1 over here as minus 1 and make it equals to 0. And I need to solve that. Okay? Solving that, I have the same as 1 equals to minus lambda times 2x, as shown here, and 1 equals to minus lambda times 2y, as shown in here. And our constraint equals to 0. So I need to solve this system. Solving this system is not that difficult, of course. You guys can just take this first equation and you can find x. X will be here minus 1 over 2 lambda. And y will be also minus 1 over 2 lambda, as shown here. Okay? If I apply this x, if I solve this constraint for this x and for this y, I will have exactly this. This is my x, this is my y. To the square, I will have this. I have to solve this constraint, which will provide lambda equals to minus 1 over the square root of 2 and plus 1 over the square root of 2. I have 2 lambdas, so I have 2 Lagrange multipliers. Okay? Each Lagrange multiplier will work on a different aspect of my problem. We are going to understand that better when we go for the support vector machine. Even before, you guys are going to understand that better. You can understand like this. I just solved for x and y to try to find plausible values for lambda. After finding plausible or good values for lambda, I just got back solving my system. What is x and what is y for this lambda minus 1 over square root of 2? And what is x and y for lambda equals to plus 1 over square root of 2? For minus 1 over square root of 2, just proceeding with the substitution, I have x equals y equals minus 1 over 2 times lambda. And I have a value for lambda. And multiply, of course, plug in lambda here, I will have square root of 2 divided by 2. If I solve for lambda equals to plus 1 over the square root of 2, I will have minus square root of 2 over 2 for x and for y. So x and y assuming this value is one solution, and x and y assuming this negative value is another solution. Going forward, When I apply those two values, x and y, in my optimization function, in my objective function, my objective will result in my z-axis. My z-axis, which is the result of my function, will be square root of 2 in this case, if I apply my function. And when I apply, again, the second solution, which is this x and this y, I will have minus square root of 2. I have already two solutions. This is actually my global maximum and this is my global minimum. You guys can see that the Lagrangian multipliers will provide every candidate solution. In this scenario, I have two candidate solutions. One providing the maximal value and another one providing the minimal value for my problem. Take a look. This is x equals to minus the square root of 2 divided by 2 and y minus the square root of 2 divided by 2, which provided as result minus the square root of 2 in terms of z, as you guys can see. This is the minimum. The maximum is here. Plus square root of 2 divided by 2 plus the square root of 2 divided by 2. X is here, y is here, and z is the square root of 2, which is the maximal value. If I look for a maximization, I will have this point as my solution. If I look for a minimization, this will be my solution. Okay? Maximization is here, minimization is here. Why it is in here and in here? Because I'm solving for the quality. If I wasn't solving for the quality, you guys can notice that I can have like a bunch of values in my surface that grow up to infinite over here and go down up to negative infinite over here if we're looking for the minimization problem. But I'm solving for the quality. Just consider a different problem now. Now we are going to have a second example, just to come up with a, let's say, a complementary point of view. Let's suppose we are maximizing this objective function, x to the square y, subject to this constraint, x to the square plus y to the square equals to 3. It's an equality constraint, okay. Can I differentiate this in terms of x and y? Yes. And this? Yes. If I differentiate g in terms of x and y, is it going to produce the zero vector? No, it's not. It's not going to produce the zero vector. This is a way of formulating it. It's quite common to find this formulation. People call it the Lagrangian formulation. You can notice that this is the same as solving this. If I have the gradient vector of f equals to minus lambda gradient vector of g, this turns out to be the same as the gradient vector of f, which I'm going to compute on top of this, okay? Plus if I bring over here, plus lambda times the gradient vector of g equals 0. If I make this equal 0, it's the same as bringing this up to this left side. This is a way of writing a single Lagrangian function, as people usually call it, in terms of my objective function and my restriction, my constraint over here. Take a look. This is my optimization function. This is plus lambda, plus because this is the same as bringing this term to this side and making it equal to 0, okay? Plus lambda times my gradient, my constraint minus 3 to make it equals to 0. This will be x to the square y, as shown here, plus lambda times my constraint minus 3, which is the same as x to the square plus y to the square minus 3 equals 0. Or I cannot even, it's not even necessary to show minus minus 3 over there, of course. Okay, 3 minus 3 is going to be 0. So I can solve for this system, and if I solve for this system, which is the same as the gradient of this being equal to minus the gradient of this, or maybe if I want to find the gradient for all this equals to 0, it's the same as this. Again, I have to ensure my constraints being satisfied, otherwise my problem is not solved. Solving this problem, this is the surface. Take a look at my objective function. This is the objective function, quite complex in comparison to the previous problem. This is my constraint. If I'm solving for the quality, it means that I can accept any point lying on the projection of my constraint onto my surface. Okay? This is the problem I'm solving, so I need to find the gradients. Okay? It's not difficult. If I apply this Lagrangian in terms of x, I will have this 2x times y, okay, which is in here, plus 2x times lambda, 2x times lambda equals 0. Remember, it has to be equal 0 because I was bringing this term of minus lambda to this side. It's going to be plus lambda, and a 0 remains on the left side after finding the derivative in terms of x. Remember, the gradient vector is in terms of x and y, okay? If I now differentiate in terms of y, what I will have exactly 2x plus 2y lambda equals 0. And if I differentiate in terms of lambda, I will have my constraint. That's quite interesting because I can see this as a problem in terms of every variable I have in my problem. Now I can have in my Lagrangian function, which is in here, if I differentiate in terms of x, in terms of y, in terms of lambda, I have my problem solved, or I have, let's say, my linear problem, my linear system of equations to be solved. When I differentiate in terms of lambda, I will have my constraint. That's simply the constraint, as you guys can see. It's easy to notice that's my constraint. What can I do? I have to solve this. I have to solve this problem. To solve this problem, if I look at this first equation here, I just have two possibilities. Either my lambda is equals to minus y to make this equal 0. Take a look. Or x is equals to 0. If x is 0 here, it's going to be 0, of course. So I have two possibilities. X equals 0 and lambda equals minus y. So I can make the proper substitutions. Then, if my x is equal to y, equals to 0, I can find y equals to plus or minus square root of 3 if I apply equation 3. And I find lambda equals 0 by applying x equals 0 in equation 2. Having lambda equals to minus y, if I solve it, I can find some other results. So with the substitution in equation 2, I will have this, okay? Then I will have x to the square equals to 2 times y to the square. And substituting this in equation 3, I can find y equals to plus or minus 1. In this scenario, I'll have a bunch of solutions. I'm not worried about this because you guys can find the solutions. You guys know how to solve linear systems. If you don't, go back to some books and study that because you're gonna need it, okay? And what's interesting here, I have a bunch of solutions, okay? Let's go to my solutions. Those are my solutions in terms of x and in terms of y. I have square root of 2 and 1, minus the square root of 2 and 1, square root of 2 and minus 1, minus the square root of 2 and minus 1, 0 and square root of 3, and 0 and minus the square root of 3. So I've got six critical points to analyze, 6 candidate solutions. Those 6 candidate solutions are shown in here. One is here, one is here, one is there, one is there. There is one solution here, guys, and there is another solution over here, guys. It's not plotted, but it's in here. Because here is an inflection point, and here's another inflection point. When this changes, this concavity given to, as you guys can see here, changes, and this convexity, this local convexity changes over here. When I apply all those values in my original surface or optimization function f, if I have plus square root of 2 and 1 or minus the square root of 2 and 1, I will have 2 as the result. This is this solution here, 2 as result, the result as you guys see, and here also 2 as result. If I apply plus and or minus square root of 2 minus 1, I will have minus 2. Those solutions are here, guys. Those 2 solutions are here. If I apply 0, take a look, x equals 0, which is in here, exactly this point, and y plus square root of 3 or minus the square root of 3, plus is here, sorry, and minus is here, square root of 3. Yes, yeah. I will have 0 as a result. If I'm looking for the global maximum points, I will have 2 solutions. If I'm looking for the global minimum points, I will have also 2 solutions. This is not the solution in neither case, okay? So if I'm looking for, for the maximals, I have 2 maximals, minimals, I have 2 minimals, not just a single solution, but 2 solutions. Now I suggest you guys to solve these 2 problems. Just stop the video and solve these 2 problems. The solutions for those are in here, as you guys can see, okay? There is a 3rd problem, a 4th problem. So we have a 1st, a 2nd, a 3rd, and a 4th problem that you guys can bring to our discussions every Friday from 10 to 12 Brazilian Standard Time in the Google Meet that I shared with you guys using TDR web system, okay? Of course, those solutions are not that difficult. There is a video here you can watch to find the solutions. But please, try to solve both, okay? After discussing the Lagrange multipliers, we can go for the Karushko and Tucker in the next video. See you guys!